All right, so in this next example, we're going to first look at the normal approximation to the binomial, and then we're going to change this to a sampling distribution. And again, you'll see how that goes in hand with each other. The Associated Press reported that 71 of Americans ages 25 and over are overweight. A researcher wants to know whether the proportion of such individuals in his state that are overweight differs from the national proportion. A random sample of 600 adults in his state results in 405 who are classified as overweight. So just to kind of go over the rule of for our binomial, B would be binary. Either a person is overweight or not. I is independent, so one person being overweight is independent from another. And again, it has to do with, even though we're not picking with replacement, it has to do with that 10% rule. So yes, that is given. Our 600 adults are less than 10% of all the adults in the state. Then we have a fixed number of trials because n is equal to 600, and our probability of success remains the same, and that's our 71% given in the question above. So we're going to check our rule of thumb, which is the n times p and the n times q. N times p is 600 times 0.71. And that is equal to 426. And then we have the n times q, which is our expected number of failures. That's 29% of 600, and that's 174. Again, both those numbers add up to our total sample size. So both of them are larger than 10. So yes, we can say X follows an approximately normal distribution with the mean equal to 426, which is the n times p, and our standard deviation is the square root of n times p times q, which is 600 times 0.71 times 0.29, and that's equal to 11.11. So yes, our number of successes is approximately normal with a mean of 426 and a standard deviation of 11.11. So this is our mean of the number of successes, and this is our standard deviation of the number of successes. We're now finding the probability that at most 405 of the 600 sampled adults are classified as overweight. And we're just going to use the simplified form. We're not using the continuity correction, which we talked about in the last section. That is really more for like extra credit. Going into inferential statistic, we're no longer going to look at a continuity correction over here. So at most, 405 means less than or equal to 405, and we're simply going to use our online calculator. Our sampling or our binomial distribution over here is centered at 426. 405 is going to be over to the left, and less than means we're shading to the left. So we're going to go over to StatCrunch and enter both our mean and our standard deviation, and we're going to look at this area. So looking at Stat Calculator Normal, putting in our mean of 426, our standard deviation of 11.11, looking at an area to the left of 405, and remember over here with the normal, we just have either to the left or to the right. If we wanted to do the continuity correction, we would just make it a 405.5. However, remember, we're no longer going to look at that going forward. That was just in that last section, and only really when you're asked to do it or maybe for extra credit. Our probability over here is 0.0294. Which is a pretty low probability. So let's see for the second part now, we're going to look at the sampling distribution. So again, looking at the exact same context. So we have 71% overweight. We are looking at a sample size of 600. And we want to know, 405 in our sample were overweight. which is actually what we call our number of successes over here. We have our sample size of 600, and again, our population proportion is 0.71. So what is the sample proportion? Well, our sample proportion is the number of successes divided by our sample size. So that's 405 out of 600. So don't confuse that with the population proportion, which is 71%. We end up with a sample proportion of 0.675, so it's a little lower than our population proportion. Now let's describe the sample proportion of overweight individuals in a sample of size 600. Well, we know it is centered at our population proportion, so the mean is equal to our population proportion, and the standard deviation is equal to the square root of P times Q over N. So our population proportion is 0.71. And our standard deviation of this is the square root of 0.71 times 0.29 divided by our sample size of 600, which is 0.0185. So if we drew a little image over here, it would be centered at 0.71. Our standard deviation is 0.0185, and we're now looking for the area of at most 405, which really relates to a sample proportion of at most 0.675. So really I could draw the image down here. So let's find this probability again using StatCrunch. And we should get a value that's pretty close to the previous one. Using the same online calculator, but we're now going to change our mean to 0.71 because our sampling proportion is centered at the population proportion. Our standard deviation is 0.0185, much smaller obviously because we're looking at values between 0 and 1. And we're now looking at the area to the left of 0.675. When we compute this, we end up with a sample proportion, or with a probability of 0.0293. All right, so our probability is 0.0293. And we can compare this with the probability we got up there, 0.0294, so you can see how close it is. The most important takeaway over here is when we're looking at our probabilities from two different angles, you can see that we can use our binomial distribution to find this probability, or we can use our sampling distribution for the sample proportion to calculate this probability. One thing you want to make sure is that you don't mix up the two, right? If you're looking at binomial, then you're looking at a mean of n times p and a standard deviation of the square root of n times p times q. When you're looking at the sampling distribution of the sample proportion, you're going to look at a mean of p and a standard deviation of the square root of p times q divided by n. So make sure you're not mixing apple and oranges when calculating these probabilities.